As a front-end developer, I'm really curious about how the everyday tools that I use actually work. And I often bump into issues where, had I known the internals of the tool I build with, the solution to it would have been really obvious. So this time I decided to learn how a Flexbox engine works in CSS. And I bumped into this really interesting blog post on the internet that helped me understand how it works. So here I am sharing my knowledge with you guys on YouTube. So here it goes. What's a layout engine though, you ask? It's basically a piece of software that automatically positions elements on a screen according to a specific set of rules and constraints. A layout engine can be something truly simple or as complex as a CSS layout engine with multiple modes. It's important to decide where we draw the line. Hence, we begin with a list of requirements for this simple project. First, we want to implement the Flexbox layout. We are not interested in any other CSS mode. We do not plan to support grid or float. Second, for simplicity, styles are not cascading. That is, each element has its own style and does not inherit from its parent or propagate it to its children. The only property that cascades is the z-index. Third, the user provides the styling for each and every element. Fourth, the width and height values, just like in CSS, can be expressed as numbers or percentages. Finally, top, left, right, and bottom behave a bit differently from CSS. Here's how it works. If the element is positioned as absolute, these properties are used to define its position relative to the parent view. If it is positioned as relative, an offset is calculated from its resolved layout position and then applied to the view without affecting its sibling views. Finally, if the width is not defined and let's say both left and right are, then the element will stretch to fill the space between the two offsets. The same applies to height and top and bottom. Now that we know what a layout engine is and what are the requirements that we'll be building it for, we can go ahead and talk about how it works. Conceptually, the layout engine takes a tree of elements with their user applied styling and returns a copy of the tree with absolute positions and resolved sizes for each element. We use this tree as a data structure to represent the parent-child relationship among these elements. The main challenge here involves calculating the absolute position and dimensions for each element. So suppose we are somewhere in the middle of the layout tree and the corresponding element has a width of 10%. To calculate the width of this element, we need to know the width of its parent, but we don't know it yet because we are in the middle of the tree. We need to go back up, calculate the width of its parent, and then go back down and calculate its width. This way, we can go down the tree and calculate the sizes of its children. So although this sounds like a recursive process, it's possible to resolve all the sizes and positions of all the elements in the tree in just 3 passes. So how exactly do we resolve the layout in a finite number of passes? Here's what happens in each pass. As mentioned earlier, we start with the layout tree. The structure of the tree represents the parent-child relationship among elements, and each tree node contains the user-applied styling. We now begin our first pass. Starting from top, we traverse the tree downwards in level order. That is, we first visit all the elements that are at the same level, then all of their children at the same level, and so on. Through this process, we generate another data structure called queue, which we will use for our next pass. In the second pass, we start from the bottom of the queue and move towards the top, resolving the sizes of parents that are dictated by their children. Now in the third pass, we go from the top to the bottom of the queue, resolving top, bottom, left, right, percentage sizes and flex values. So this was a high level overview of the algorithm. Now before we go ahead and show how the actual algorithm is implemented in the next video, let's discuss what are the required data structures and types we'll be using in our algorithm. Let's start with trees. We would use this to represent the parent-child hierarchy of our elements. Okay, let's begin by creating a generic class called tree to represent a single node in a tree. It would store instances to 5 other tree nodes, which are 1. Next, it stores reference to the next tree node in the same level order. Second is previous, which stores reference to the previous tree node in the same level order. Parent, which stores reference to its parent. First child, which stores reference to the first child of this tree node. Last child, which stores reference to the last child of this tree node. Now since all these instances are themselves tree nodes, they store references to their own previous and next tree nodes, which are in their same level order. Tree class also has a method called addChild, which takes in a node and adds it as its last child. Queue. We'll use queue as a data structure for tree traversal. But first, we'll start by defining an interface called queueNode to represent a single node inside a queue. This interface holds reference to its data, to the previous node in the queue, to the next node in the queue. To represent the queue itself, we'll create a generic class called queue. It would hold instances to the start node of the queue, to the last node of the queue, and a variable to store the total size of the queue. Queue also has 3 methods to add and remove queue node from it. enqueue, which adds a queue node to the start of the queue, increasing the size of the queue by 1. dqueue, which removes a queue node from the end of the queue, decreasing the size of the queue by 1. dqueueFront, which removes the queue node from the start of the queue, decreasing the size of the queue by 1. Now that we have our basic data structures defined, let's also define some types to represent the kind of styling properties that our layout engine would support. In this project, we won't be dealing with any styling properties other than those which are directly related to layout. Hence, in view style, we are skipping visual styling properties like color, border radius, but would instead support just one background color. Also, our engine will provide some basic text support. This brings in an additional complexity of having to support dynamic sizing of parents wrapping their children based on their widths. For example, buttons, whose width are dependent on the width of the text that they enclose. Type for text style is much simpler than view style. Let's also define another type called fixed view that would be used to store all the resolved absolute positions and sizes. It would also store a reference to its corresponding view style or text style. So that's it for now. I'll be covering the actual implementation of the algorithm in the next video. So see you there. Thanks for watching. Bye bye.